Hi folks, in today's video we are going to be starting organic chemistry and learning about molecular orbitals and hybridisation. So what is a molecular orbital? So molecular orbital theory is used to describe how atomic orbitals, combine when atoms produce molecules, or atoms to produce molecules. Molecular orbitals are responsible for your shape, double, triple bonds, and it also explains how some molecules are coloured. Specifically organic molecules. Now before we've only learned about transition metals being coloured, whereas now we're going to learn about organic molecules. So basically an atomic orbital is an atom. Okay, that's to do with atoms. And then a molecular orbital, that is to do with electrons within a molecule. So molecular orbitals can be used to explain different types of bonds. So we're going to start with this one here called a sigma bond. As you can see, a sigma bond is a bond formed by an end-on overlap of atomic orbitals, and they're lying on the axis of your covalent bond. So we've got a little diagram here. Two s orbitals join to make a sigma bond. So if we take them both to be hydrogen, they'll combine together to create hydrogen as its diatomic element or the diatomic molecule. Sigma bonds aren't specific to the s orbitals. They can be a mixture of s and p's, two p's together, and p's and d's from these diagrams in the bottom. Let's have a look at your s and your p. You can see this bit that I'm colouring in. Again, it's on the end. Same with your two p's, it's on the end here. Don't worry too much about your d orbitals. We don't really need to know about them in advanced higher, but it's just something you should be aware of. If you want to have a look at the middle, we've got this little thing here called Sp. This is something that we're going to be learning about later on in the video. It's something called hybridisation. So the molecular orbital is going to be slightly different from your atomic orbitals. Again, it also contributes to the shape. So let's go back to that little example. We've got hydrogen here, to make our H2. So we've got our s orbitals form this new molecular orbital. So for shorthand, we're going to call that MO. Now what we can do is they're going to do something different. So the molecular orbital is going to be slightly different in energy than the separate s atomic orbitals. It's actually lower in energy because they are relatively happy being together. So we can draw a nice little diagram here where this is increasing energy. We can take, oops, this is easy, make that straight. Here we have our s orbital, and I've just told you that they make something lower in energy, and this is your sigma bonding molecular orbital. It also makes something higher in energy as well. Now we can call that the anti-bonding orbital. And instead of being a sigma bond, we call it a sigma star, just to identify between the bonding and the anti-bonding. The anti-bonding is higher energy. It usually is empty. It's also less stable. So electrons tend to want to form this bonding one down the bottom. They'd rather not form your less stable anti-bonding molecular orbital. Molecular bonding orbitals occupy the space between two nuclei. So each orbital can accommodate two electrons, and that's the basis between bonding between atoms. Unfortunately, it's not that simple. Further down the periodic table, things start to get a little bit complicated. Basically, as you get to the second row, you've got both 2s and 2p orbitals. This explains the shape of alkanes that you're familiar with from National 5 and higher. The shape of alkanes can be explained by something called orbital hybridisation. So I've got a little definition at the bottom. It said this theory assumes that the 2s orbital and 3p orbitals hybridise, which is another word for mix, to form 4 new orbitals known as sp3 orbitals. So again, that is 1s orbital and 3 p orbitals, and they make your 4 sp3 orbitals. So again, a 1s and 3p. So we're starting with 4 on one side and we're starting with 4 on the other side as well. What does that look like? So if you have a look at my little diagram here, I've got my 2p orbitals with 2 electrons. I've got my 2s at the bottom with 2 electrons, and again 2s has got less energy in it than 2p, that's why 2p is slightly higher. They create this new hybridized orbital called your sp3. So it's slightly lower in energy than your 2p, slightly higher in energy than your 2s. All of the 4 orbitals are degenerate and they have identical shapes. Now again, that's a little recap from earlier on. That means they have of equal energy. Another new type of bond is something called a pi bond. Now this time your atomic orbitals overlap side on. And a pi bond occurs when atoms form multiple bonds. So what that means is double bonds. Okay, double bonds between carbon atoms, oxygen for example. If you have a look at my little diagram here, you'll see that we've got side-on overlap. Now you need to form a sigma bond first in order to form a pi bond. You know, they don't come separately. A pi bond has to have a sigma bond attached as well. And because of that, your orbitals available for your pi bonding they only really can partially overlap, so they form a slightly weaker bond. So in that case, sigma bonds are much stronger than your pi bonds. Just if you have a look again at the diagram, you've got your side-on overlap versus your end-on overlap as well. So it means that your sigma bonds are more stronger than your pi bonds. Pi bonds are in alkenes, but again they don't help explain the shape. There's got to be some sort of hybridization going on, because if not, ethene would technically be tetrahedral, even though we definitely know it's not. Instead, we make something called an Sp2 hybridized molecule. And again, from the little diagram, it should say 2s and 2p orbitals hybridized to make one, and the other p orbital remains unhybridized. So what is a Sp2 hybridization? 1s and 2p orbitals. So here's a little summary. Sigma bonding occurs when 2 atomic orbitals overlap end-on. Pi bonding occurs when 2 atomic orbitals overlap side-on, and your sigma bond is stronger than your pi. Sp3 hybridization occurs from 1 2s with 3 2p's. Sp2 hybridization occurs when 1 2s is mixed with 2 2p orbitals. And then you've got a little table at the bottom explaining that a carbon-carbon single bond is just 1 sigma. A carbon-carbon double bond is a sigma and a pi. Carbon-carbon triple bond is a sigma and 2 pi bonds. Okay, I've got a question for you. Feel free to pause and answer this question. Here we have a structure of quinoline, and I want you to tell me how many sigma and pi bonds are present in this molecule, please. Just to finish up, I'd like to mention a very important compound called benzene. Benzene's an aromatic compound. It has the chemical formula C6H6. And aromatic compounds contain a ring of delocalized electrons. That should say, not electron. And that's because they are due to hybridization. If you make benzene, or if you have a look at any pictures of benzene, it's a planar molecule. It's got bond angles of 120 degrees, so it can kind of lie flat on the table. So why can't it lie flat on the table? Well, you've got your double bonds between your carbons. They're sp2 hybridized. They're also joined by sigma bonds. Again, this is something we've just met earlier on. A kind of weird donut shape is formed above and below the plane of the carbon atoms. Because you've got so many pi bonds going on, they kind of merge together to make this donut shape above and below the plane of carbon atoms. So within them, you've got delocalized electrons. And that's our little introduction to molecular orbitals, sigma pi bonds, and sp3 and sp2 hybridization finished.